EDX Decision 1 algorithms, sorting, packing and other algorithms. Sorting algorithm using the Quicksort algorithm. We may want to sort a list of numbers into ascending order or descending order, or a list of words or letters into alphabetical order, and we need to check the order required in a particular question. We might do this because we need a sorted list to perform some other algorithm. For example, the first fit decreasing algorithm requires the items to be in descending order before starting. For this specification, the two algorithms that you need to learn are the bubble sort algorithm and the quicksort algorithm. The quicksort algorithm is generally more efficient than the bubble sort algorithm. It requires looking for a midpoint of the list and using that as a pivot element, and this is used to create two sublists during the process. In general, for a list of size n, the midpoint can be found by using the half n plus 1th term, and this can be rounded up if a decimal value is produced. So for example here, in this example, we have 4, 5, 6, 7, 8, 9 items. So our mid value would be 9 plus 1 over 2, which should be the 5th item. So 1, 2, 3, 4, 5, that is our mid value. In this example, we have 4, 5, 6, 7, 8 items. So we get our mid value as 8 plus 1 over 2. So that gives us 4.5. So we would round up to get the 5th item. 1, 2, 3, 4. That would be our mid value. And just a word of caution, some exam boards and textbooks will choose a different pivot or mid value element as their starting point. So the quicksort algorithm. Step 1. Select the pivot element from the list, or the midpoint. Step 2. Write down all the numbers that are smaller than the pivot in a sublist to the left of the pivot, making sure you keep them in their original order, and write down all the numbers that are larger than the pivot in a sublist to the right of the pivot point, keeping the numbers in their original order. Step 3. Apply step 1 and 2 to each separate sublist until each sublist contains only one number. So in this example, we're going to sort this list of numbers into ascending order. So first thing we do is we note how many elements. So there's 4, 5, 6, 7, 8 elements. 8 plus 1 over 2 is 4.5. Which means our mid value or pivot point is the 5th element. 1, 2, 3, 4, 5. I'm going to use the convention of underlining pivot points, and I will circle elements when they become fixed in the correct position. So now all the numbers in the list that are smaller than 11 go to the left, and all the numbers bigger than 11 go to the right. So 5 is smaller than 11, 8 is smaller than 11, 3 is smaller than 11, 7 is smaller than 11, 6 is smaller than 11, and then 11 itself. 12 is bigger than 11, and 15 is bigger than 11. Because all the numbers smaller than 11 went to the left, and all the numbers bigger than 11 went to the right, 11 must be in the correct place, and I'm now going to circle it. We now have two sublists. We've got a sublist there and a sublist of 5 elements at the beginning. The algorithm says, look, we're going to do both sublists in the same iteration, and we need the pivot point. So here we have a sublist of 5 elements, and when we apply our rule, or just by inspection, we can see that 3 is a pivot point, and here we've got 2 elements, which means our pivot point is going to be at the place called 1.5, and when we round that up, that would be the second element, so 15. So we've got 2 pivots. So doing this first sublist, we know 11's in the right place, so you can put that in straight away if preferred. So looking at our pivot point of 3, all the numbers in the sublist smaller than 3 will go to the left, and the bigger numbers will go to the right. In this example, there are no elements smaller than 3, so nothing goes to the left of 3, so that means we position our pivot afterwards. All the remaining 4 elements are bigger than 3, so they follow 3, so that would be 5, 8, 7, 6. Make sure you keep them in their original order. 12 is smaller than the pivot, so 12 stays to the left of 15, and that 15 is now fixed, and 3 is now fixed. So now we've got 2 sublists. I don't need to do this sublist because it only contains 1 element, and the algorithm says you can stop when all sublists contain just 1 element, so that bit we can leave. Here we have 4 elements, and the mid value, or the pivot point, is going to be at 2.5, which rounded up gives me the 3rd element. So there is my pivot point. 3 is fixed, 11 is fixed, 15 is fixed, and 12 is on its own. So the elements smaller than 7, 5 is smaller than 7, 6 is smaller than 7, then we have our pivot, and the element that is bigger than 7 is 8. So that means that 7 must be in its appropriate position, so I can circle that now to say it's fixed. I don't need to apply the algorithm to an element on its own, so the 8 and the 12 don't need an algorithm, but I do have these 2 elements together, and the convention is that 6 would be my pivot, so I'm going to underline that to make it clear. 3 is in the correct place, 7 is in the correct place, so is 11, and so is 15. I don't need to worry about a list of 1 element. So 6 is my pivot, 5 is smaller than 6, so 5 stays to the left of 6. So that means the pivot 6 must be in its correct place. So I'm going to circle it so I know it's in its correct place. And the algorithm says stop when all the sublists contain just 1 element. So I don't need to do a 5th pass. All my sublists contain a single element, so I can now stop. And we've got everything in order, as you can see, 3, 5, 6, 7, 8, 11, 12, 15. So example 2, I'm going to organise these numbers into ascending order, and you can see that they are in reverse order. So we should see here how efficient the Quicksort algorithm is at sorting out a reversed list. So we've got 4, 5, 6, 7, 8, we've got 9 elements in the list, so 9 add 1 over 2 is 5, so the 5th element is my pivot. So 1, 2, 3, 4, 5, so there's my pivot, so I'll underline it so I know it's a pivot. All the numbers smaller than 5 will go to the left of 5, and all the numbers to the right, bigger than 5, will go to the right. So 4 is smaller, 3 is smaller, 2 is smaller, 1 is smaller, and there's my pivot. 9 is bigger, 8 is bigger, 7 is bigger, 6 is bigger. So that means that 5 is in the correct place. I'm going to circle it so I know that it's in the correct place. Now I need new pivot points. So I've got 4 elements in this sublist. So the rule gives me 2.5, which when rounded up gives me the 3rd element. So that 2 is my pivot. And likewise here, 7 would be my new pivot. So looking at this sublist at the beginning, anything smaller than 2 goes to the left of 2 and bigger than 2 to the right of 2. 1 is smaller than 2, then the pivot. 4 is bigger than 2, 3 is bigger than 2, and we know that 5 was in the correct place. In this sublist, anything smaller than 7 goes to the left, and anything bigger than 7 goes to the right. So 6 is smaller than 7, then the pivot. 9 is bigger than 7, 8 is bigger than 7. So 7 can be circled, it's now in the right place, and 2 can be circled. So I now look for new pivots. We've got 1 on its own, so that doesn't require a pivot. We've got elements 4 and 3 in a sublist, 3 will be the pivot. And we've got 9 and 8 in a sublist, 8 will be the pivot. So if you want, you can put the 2, the 5 and the 7 down first. 1 is an element on its own, so we don't need to worry about that. 6 is on its own, we can leave that one. So 3 is my pivot in this sublist. There's nothing in this sublist smaller than 3, so the pivot starts the list off. 4 is bigger than 3, so that goes to the right of 3. There's nothing smaller than 8 in this sublist, so 8, the pivot 8 starts it off, and 9 is bigger than 8. So 8 must be in the correct position, and 3 must be in the correct position, and all my sublists, 1 is on its own, 4 is on its own, 6 is on its own, 9 is on its own, so the algorithm says stop when all the sublists contain a single element. Just a word of caution, there are many videos on Integral and on YouTube looking at these algorithms, and make sure you choose the algorithm that is appropriate to this process and this exam board. In the next session, we're going to be looking at the efficiency and order of algorithms.